Okay. Okay. Hi, everyone, and thank you for attending this session of the workshop, and especially those in Europe. It has been very late for you in the night, right? So, yeah. So today, the topic of this session is about energy decomposition analysis, and energy decomposition analysis (EDA) is a type of computational method specifically for studying non-covalent interactions. As we all know, non-covalent interactions are playing an essential role in like many areas of modern chemistry, including like molecular catalysis, enzyme catalysis, like a protein ligand binding, and so forth. And if just imagine how you would like to study like non-covalent interaction using quantum chemistry. So probably the first like a go-to method to use is the so-called like a supramolecular approach. So what you do is you do a calculation for the intermolecular complex AB and then subtract the energy of each of the monomers, and then you get this interaction energy. This method can give you this number, which is called the interaction energy. It is a monolithic number, which doesn't really have too much like a physical insight, right? So the goal of the energy decomposition analysis method is to further separate this term into a couple of physically more intuitive like components to help you interpret the computational result. So in the energy decomposition method we are going to talk about today, we separate the total interaction energy into 5 different components, including permanent electrostatics, Pauli repulsion, dispersion, polarization, and charge transfer. So each of these terms have some sort of like associated physical meaning. And so the energy decomposition analysis method can be used to do quite a lot of things. For example, like it can help interpret to figure out some nature of specific non-covalent interactions, especially some like not so common ones. And like, for example, like a halogen bonding and like a cation pi interactions and so forth, right? And also this EDA method can really help understand the role of non-covalent interactions in a lot of chemical processes. For example, in a catalysis research, you would like to figure out how each energy component can help stabilize the transition state. And this probably can give you some insight to help you do the catalyst design. And for theoretical and computational chemists, this EDA method can help the development of other theoretical models, such as force fields and machine learning potentials. So the method we are going to talk about today, and yeah, the EDA method in Q-Chem is called absolutely localized molecular orbital EDA, ALMO-EDA. So to achieve this decomposition of intermolecular interaction energy, this ALMO-EDA method will introduce 2 intermediate states to connect the initial state, which is like the isolated fragments, and also the final state, which is a fully relaxed complex. So the first intermediate state is called the frozen state. So in this state, you just bring these monomers together into the complex geometry, but the molecular orbitals of these monomers are not relaxed. It's frozen just in the isolated monomer state. So in that way, the energy difference between this frozen state and the isolated monomer state is defined as a frozen interaction energy. Then the second intermediate state, in the second intermediate state, we allow the molecular orbitals on each of the fragment to relax in the presence of the other fragment, but we do not allow the mixing of the molecular orbitals on each fragment. So in this way, the molecular orbitals on each fragment will be polarized. So this is called the polarized state. And the energy lowering from this frozen state to this polarized state is defined as a polarization energy. And finally, the energy basically we remove all the constraint and allow the system to fully relax. And the energy lowering, the further energy lowering is defined as the charge transfer because because at this step we allow the charge to be transferred between fragments. And here what we are decomposing is called the interaction energy. So it's the energy difference between the complex and also the monomers in their geometry as in the complex. And if we are decomposing a slightly different quantity called the binding energy, which is energy between these complex and the sum of energies of fully relaxed monomers, then we will have an extra term called geometry distortion, which accounts for the energy penalty for each fragment to form a slightly distorted geometry as in the complex. And starting from 2015, there have been several advances in this ALMO-EDA method, which gives rise to the second generation of the ALMO-EDA. So in the second generation of ALMO-EDA, the interaction is decomposed into 5 terms, as we mentioned at the beginning of my presentation. So the first advance in the ALMO-EDA is we allowed the decomposition of the original frozen interaction term into 3 components: permanent electrostatics, polyrepulsion, and dispersion. And this helps with the interpretation of computational result further. And there are 2 flavors to achieve this decomposition. And for details, you can refer to the Q-Chem menu. And the second approach, second advance is the introduction of this fragment electric response function approach. So this provides a more robust method to separate the polarization and the charge transfer. And now with this method, this separation can have a well-behaved basis set limit. And the third advance is more recent from the Hadgarden group at Berkeley. So this is called the non-perturbative charge transfer and polarization analysis. So with a non-perturbative polarization analysis, you can now further decompose this polarization term and figure out how much polarization energy each fragment contributes. And for the non-perturbative charge transfer analysis, you can decompose this charge transfer term further into a pairwise contributions. So for example, for this dimer system, you can figure out how much charge transfer comes from the A to B donation and how much is from the B to A donation. In addition, associated with this method, there is analysis method called complementary occupied virtual pairs, COVP. So this can help you generate an orbital picture for this polarization and also charge transfer analysis. So here it shows the 2 COVPs involved in the charge transfer for this base pair. And yeah, one of the core developer of this method, Heng Yuan, is actually a TA here as in this workshop. Okay, and and this is another important extension of the second generation ALMO-EDA, because the majority of chemical processes people care about happen in a condensed phase environment, in solution. So we developed this method called ALMO-EDA solve. Basically, we just allow the ALMO-EDA calculation to be performed with an implicit solvent model like PCM or SMD. And typically, the primary effect of the solvation is the damping of the electrostatics. So you will find some quantitative difference in the interaction and also the components. So I want to now show a couple of examples from previous publication. So this is an example from the original ALMO-EDA 2 paper. And here we are using the method to investigate the interaction of two configurations of the adenine-thymine complex. So for the hydrogen bonded complex, after you run the EDA, you will be able to tell the interaction is dominated by electrostatics with also non-trivial contributions from the other attractive interactions, including dispersion, polarization, and also charge transfer. While for the stacked configuration, it's a pi-pi stacking, right? So here, as expected, as dispersion interaction plays a most important role, but also there is a significant contribution from the electrostatic interaction. This is probably not that intuitive. And this is another more recent application of the solvated version of ALMO-EDA. Here we are just investigating the substituent effect on the binding of CO2 on this CO2 reduction catalyst. So here the y-axis shows the EDA result, subtracting the reference result of the unsubstituted complex. So here we can see that with both substituent groups, we get enhanced binding of CO2 because this number is negative for the total interaction, delta E, okay? But they actually arise from different physical origin. So for this TMA, trimethyl amino group, this mostly comes from the reduction of polyrepulsion, while for this one, it mostly comes from the favorable enhancement of electrostatics. And the EDA method we just talked about is referred to as a vertical EDA method because the typical approach is you first optimize the geometry of your system. So you get here, and then you do an EDA calculation, and the energy components are shown by this dashed line. And here we are introducing another picture for doing the energy decomposition another way. So here this method is called adiabatic EDA. What we do is we relax the complex geometry on each of these intermediate surface, and potential energy surface, including the monomers and also the fully relaxed state, the initial and the final states. So we optimize the geometry, and then the energy component will then be defined as the energy difference between the stationary points on each of these surfaces instead of calculating this on this vertical line, right? But more importantly, this adiabatic EDA method allows you to further decompose the shifts in molecular properties, for example, like a change in a bond length or the change in a vibrational frequency, into contributions from frozen, polarization, and charge transfer. So here is a prototypical example showing the water chloride complex, and what you can see here is basically the near linear hydrogen bond angle, as well as the significant red shift in this OH vibrational stretch. The red shift, right, only comes mostly comes from the charge transfer, because you don't really see this large red shift before you turn on charge transfer in your calculation. And this is a new feature of the Q-Chem 6.1. So we so this is also a contribution from the Hadgarden group, and they extended ALMO-EDA approach to the decomposition of intermolecular forces. So the idea is to differentiate. So originally we have this equation, everything is like a delta E, right? But now you just take a derivative with respect to the nuclear position, then basically you get the decomposition of intermolecular forces. So here, this term, the van der Waals contribution includes both Pauli repulsion and the dispersion. So the non-electrostatic part of the frozen interaction, basically. So let's look at example of this method. So this method is called force decomposition analysis, FDA. It has been documented on the Q-Chem manual as well. So these are some examples on the paper. Let's just, for the sake of time, let's just look at one example here. So here we are looking at the force along this OH bond. So the H is a hydrogen bond donor. So what we can see is the net force on this bond is positive, which suggests there is a tendency to stretch this bond. And if you do the decomposition, you can get the contribution from different components, and these all come from the interaction with chloride anion. And you can see actually charge transfer has a most prominent contribution here. So this method can be used to decompose like forces in intermolecular complexes along the internal coordinates. The use of internal coordinates makes these forces like more chemically intuitive, right? And to run this method is pretty simple. You just need the job type force and FDA equals true in Q-Chem. So now I want to briefly talk about a few things of the job control of EDA. So first, because to simplify the job setup, we offered a couple of like these option sets. So the option one correspond to frozen interaction, frozen decomposition plus a FIRF method for polarization. And the option two correspond to the frozen decomposition plus the original ALMO polarization. And in general, my suggestion, first, we should always use a dispersion corrected DFT method to do these EDA calculations. Otherwise, the dispersion term is not meaningful. So some recommended functionals include omega B97X or M-V, and also something like a B3lib D3BJ, which is a very commonly used functional, I think. Yeah, and option one is recommended for small to medium systems with a large basis set. And option two can be used for larger systems where only double zeta basis sets are affordable, because the FIRF method doesn't really make a big difference for a smaller basis set. So that's my recommendation. And there are a couple of other keywords. Probably for the sake of time, I will not go through all of them in detail, but they are all like documented on the Q-Chem manual. So let's look at some example jobs. So this one, I probably can go through very quickly. So it is for the water interaction between water and the sodium cation. And here we just need a job type EDA, and we choose the option one for this calculation. And we turn on the Solvation model SMD to model the Solvation environment. And you will see some of the details on the slide for the practice. It is pretty similar to this example. But here, these arrows will help you find the numbers you need, right? Okay, and so I want to actually spend a little bit more time on this example, which is a new feature of the Q-Chem 6.1. Basically, we integrated the non-perturbative polarization and the charge transfer analysis with the EDA2 toolkit. So this is for a calculation of the for a complex between the carbon monoxide and this beryllium oxide. Okay, so here the basic setup is the same as the previous example, but here we turned on the polarization and the charge transfer analysis, and also turn on the COVP analysis to get the orbital picture. So first, let's look at the polarization analysis. So you can see, based on this result, the fragment 2 contributes much more energetically to the polarization, and that corresponds to the polarization of the CO molecule. And from the COEP analysis, there is only one most significant contribution, and that, if you visualize these orbitals, correspond to the electron rearrangement of the CO's lone pair. Okay, and then we can move on to look at the charge transfer analysis result. So here, the way to read these matrices is you find the off-diagonal terms, and to find the off-diagonal terms, and so here the number at row 2 and column 1 correspond to the 2 to 1 charge transfer, and correspondingly this one correspond to the charge transfer from fragment 1 to fragment 2. So, and these correspond to the transferred charge. Okay, so, and also we can do a COVP analysis associated with this non-perturbative charge transfer analysis. So here there are 3 most important COVPs based on the energy contributions. So the first one corresponds to the sigma forward donation from the lone pair of CO to an empty orbital of the beryllium, and there are 2 pi back donations corresponding to this, and I'm just plotting one of them. The other one is just from the pi bond orthogonal to this one, and you can see it is from the from the right to the left. It is a back donation to the pi star orbital of the CO, and probably I can go through this quickly. So this is for the adiabatic EDA. So what we need is just to set the frozen geom if we are optimizing geometry on the frozen surface, and the pole geom will give you the geometry on the like a forces on the polarized surface. And so here is an example showing how to optimize the geometry and calculate the frequency at the optimized geometry on the frozen surface. And we can do this for each of the potential energy surface involved. And this is the final result. Basically, what is shown here is there are 2 competing effects. So the electrostatics and the polarization, and they contribute to the bond shortening of the CO and a significant blue shift, which is, and it's most blue shifted on the polarized surface. Then when charge transfer is engaged, it is a red shifting effect. It brings down the frequency back to something closer to the origin. But in the end, the blue shifting effect is still more significant. So finally, the complex, the CO shows a net blue shift of about 30 wave numbers. So so probably I talked for a little bit too long, but here is the exercise. So the exercise is just a calculation for this complex water chloride, and it is a vertical EDA calculation using the EDA2 equals 2 option. And here we will add a couple of things such as a basis set correction, and also the non-perturbative charge transfer analysis. And we have we want you to compare the results calculated in vacuum and also in the solvent model, solvation environment captured by the SMD model. And so I think that's all for me. And